series of 2D materials, a new family of 2D materials called MXene that seems to be very promising for some applications, specifically in electronics and printed electronics. And that's over to you, Hyunho.
Okay, good afternoon, everyone. I'm glad to give you a presentation about the MXene inks for the electronic application. The first half of the presentation will be an introduction to MXene, and the second half will be what can be done with MXene and also the potentials of MXene inks for electronic applications. So the MXenes are obtained by ternary hexagonal layered material, max phase. And from the max phase, we selectively remove the A layer. So the name MXene comes from this max, removing the A, and the ENE comes from the graphene. So we call it MXenes. So the max phase is the composite of M, which is a transition metal, and A is group A element, which is normally aluminum so far, and X is carbon and nitrogen. And here the interesting thing is the MX bond here is a covalent bond, while the MA bond here is a metallic bond. And once they go into a fluorine containing acidic solution, the fluorine attacks the aluminum, and we can remove this A layer, and it ends up with a multi-layer of these MXenes. And further, we can exfoliate each layer by involving in ion or molecular intercalation and also ultrasonication. And the MXene is reported first in 2011, and now it has been already 10 years, but still there is many things to be explored. And from this periodic table, there are a number of choice of early transition metal, and also A layer, and also the carbon or nitrogen, and each component can be also solid solution. So in principle, there are numerous possibility of new MXenes in this large family. So the structures of a MXene can be divided into how many metal layers in this MX structure, and also if the metal layer is made of a mono element or the two element in solid solution, and for some specific composition, they can create an ordered structure where one atom are located on the very surface of nanosheet and the other is in the middle area. And this is related to their entropy. And recent study is trying to involve 4 different metal atoms and create like a really randomly placed high entropy MXenes. So there are so far more than 40 MXenes are reported in experimentally, and we are expecting more MXenes to be found in short time. So the synthesis of a MXene that we are using is basically we use a hydrochloric acid and involved with the lithium fluoride salt. So we can form an in situ HF in the solution. And this in situ HF will do the selective chemical etching of the max phase. For example, titanium-3, aluminum-carbon-2, and we remove the aluminum by the etching. We have a titanium-3, carbon-2 MXenes. So here is a schematic image of the crystal structure. So from the max phase, we remove the A layer, and while they remove the bond between M and A, this surface transition metal wanted to saturate the stem cells, so they try to create a surface functional group from the environment. So using this water-based route, the majority of the surface functional group is oxygen and hydroxyl and some of fluorine. Once we involve a lithium, for example, lithium cation intercalation, this lithium is positively charged, and also the surface of a MXene is negatively charged. And this involves the dipolar water molecules to be intercalated together into the multi-layer system, so we can exfoliate the MXene by repeated washing in water and also centrifugation. So for titanium 3 carbon to MXene, it can be described as a combination of a conductive carbon core and also a transition metal oxide or hydroxide-like surface in their two-dimensional shape. So they can be conductive and hydrophilic at the same time. So this makes them very unique over the graphene or graphene oxide, reduced graphene oxide family. And their hydrophilicity and conductivity and the ability to intercalate ions and molecules make them promising in majority in the supercapacitor or other energy storage applications. But we thought these properties are also very important for the electronic. And given the fact that the surface chemistry and the MXene composition will affect their properties, it can be used for electronic application. And for M to C type of MXene, like metal to carbide or metal to nitride, in metal to carbide, for separate transition metal and 3 different surface functional groups, the simulation studies reveals some MXenes could be potentially semiconductors with open band gap, and most of them are metallic, and very few can be a topological insulator. While the nitride MXenes can have potential for magnetic application due to the extra electron from each nitrogen atoms. And the surface functional group control is the key to realize the different properties from the surface functional group. And research study in Science reported they could create a 100% surface controlled MXenes by using molten salt approach. So for example, for sulfur or selenide, terminated niobium carbide MXene could show a superconductivity, while there is no superconductivity for non-terminated or oxygen-terminated MXenes. And at the same time, these two MXenes shows a different work function, where the tunability is 0.7 electron volt, and both of them are electrically conductive. And from here, I will show what we can do with the MXene for electronic applications. So MXene could be synthesized in water at the beginning, and here the image is the diluted the solution. So they show a different color because of the different absorption band. And we can centrifuge at high speed to separate the nanosheets in water. We redisperse into a different organic solvent, and we repeat this process around 3 times. We can assume that most of the water is removed from the solution, and MXene is suspended in the organic solvent. The one drawback for the water-based solution is that it can go high concentration, but it is rather weaker for the oxidation at room temperature. But once MXene is dispersed in organic solvent, it is free of oxidation and also free of aggregation. So in long-term use, the organic solvent can be a better way to store or use the MXene. So, and we found the NMP and DMF and DMAC can have a high concentration of MXene, while the alcohols or propylene carbonate and acetonitrile can allow a moderate concentration of MXene. So water-based MXene can be used by spray coating or vacuum filtration to create the thin films, or for high viscosity solutions, for example, at higher concentration or with some additive. We can use a bar coating and screen printing, which is under development. And these MXene solutions also can be patterned by conventional photolithography, or we can instead of the lithography technique, we can use direct patterning such as inkjet printing or screen printing. And the organic inks are better in oxidation resistance, and it also offers a better material compatibility. For example, if you have a water-sensitive material, you can use a water-based solution, and it's the same can be applied for polymers. So here is some images of vacuum filtrated paper samples and the cross-section SEM images. For this titanium 3, oh, there is a mistake. It's a titanium 3 carbon 2. And this can go up to 20,000 Siemens per centimeter. There is the highest value reported so far. And the cross-section images shows that there could be some gaps between the sheet. After thermal anneal, they can kind of sinter each other, so it becomes much compact. And when we see the electrical conductivity trend over the temperature, we can obviously see the high increase at certain temperature where the water and intercoolant get removed. MXene solutions can be also spray coated to create a thin films that is a transparent and conductive. So in the optical point of view, it's a little better than graphene, but it's harder to beat an oxide material or metal nanowires. But at the same time, MXene has its own advantage of flexibility. And when we tested the flexible operation, when we bend the thin films into a bending radius of 0.25 millimeter, it still shows a nearly similar resistance value, which is only 3% difference from the beginning. So that means the freestanding MXene paper can be mechanically weak, but once it is supported by a substrate, they can create a new path under strain, so it can maintain low resistance. And MXene was used as a electrode material for the oxide thin film transistors. So here the MXene is used for the bottom gate structure and also top contact pad. So these are patterned by lift-off technique. So you can see here is a MXene and here is a MXene, and some other thing you see around is from the bottom. And there's MXene allowed a nice device operation for both N-type zinc oxide and P-type SNO. So we reported it as advanced material, and we could also go for CMOS. And later we tried to pattern MXene by dry etch approach. So we could make a nicely patterned MXene array, and then we combined this with laser-fired quantum dot, because the quantum dot cannot be used after contact with water. So we go first with the MXene pattern in this approach. So using ionic gel, gauging the device operates pretty nicely with very small hysteresis, and most importantly, very small threshold voltage. So comparing this device with a gold electrode, we obviously see a reduction in the threshold voltage. And this could be originated from the lower work function of MXene. There is a 4.44 in ultra-high vacuum, and that gives a smaller barrier to the 4.14 Rumo of the lead sulfide quantum dot treated with metal ammonium iodide. MXene can be also added into a hydrogel, which is a polymer containing a lot of water inside. So it gives a combination of a nice stretchable and self-healing ability of the PBA hydrogel, and at the same time it becomes electrically conductive. And once there is a strain applied to the hydrogel, the network, MXene network in the hydrogel, gives a response that is asymmetric to the strain direction. So this allows a very nice sensitivity over a touch or even human pulse, or it can also be used for the recognition of a different vocal sound. And here is the summary of the MXene for electronics. So the surface termination of MXene and their structure and metal element, and how we etch the HD, max phase, these all impact to the properties of MXene. And for electronics, it can be used a wide range of application from like transistors or display, thermoelectric and sensors and photodetectors and plasmonics and so on. And we would like to try this, use this MXene and for wearable and flexible electronic application and possibly combined with other 2D material. And this is what I prepared for today, and I would like to thank you everyone, and also Dr. Felicia Torresi in my group and other members here, and also CPE for this nice chance for the presentation today. Thank you very much, and I would like to have some questions.
Thank you, Hyunho. Any questions? Anyone? I have just a quick one. I mean, you showed a very big change in the work function of MXene going from